Hello, Ross Finlayson here. December 19th, 2023. Another edition, an installment, an essay in words of descriptive differential dynamics. So today what I thought I would do was continue with the stacks. We left off kind of going into the stacks. We talked about Hegel, Wittgenstein, and Greek science, and it started with the talk about the dynamis, the potential, the energia, the energy of things, kind of its capacity to do work is what that is in a sense. Action, the principle of least thereof, and otherwise about causality, these being the kind of least principles that assign a determinacy to things, and any kind of reason to consider that logic makes sense by itself. For you and me both. We talked about the objective-subjective distinction, and we talked about, or for my maybe some usual viewers, we talked about these things of the Hegel's dialectic, the thesis, antithesis, and synthesis. We talked about Russell's retro thesis a bit after Frege, Gottlob Frege, and the foundations of arithmetic. So foundations is kind of the key touchstone of this kind of study. So what is foundations? Well, foundations is a foundation. It's the base, the ground, the fundament of what then we kind of have this tower, the ivory tower, if you will, academia, theory, theoria is our contemplation in this space, the tower and metaphor and reign, that the foundations is the fundamental in the theory. And with regards to the universe of logical and mathematical objects, that it's the foundations for what result hard sciences or theories of what are also called the natural sciences, physics, where basically then that kind of arises in the field. There's philosophy, there's logic and mathematics above that, then there's physics above that, and then all such fields of physics like chemistry and more physics are above that. There's an entire world, of course, of the world of the metaphor and the human condition. The soft sciences aren't necessarily soft. And above science, we have statistics, and it really is so for like the whole question of the observer and indeterminacy, or it's called Heisenberg uncertainty, and all these kinds of things kind of reflect at the same time that it's just part of the statistical hypothesis. So the scientific method and the statistical method, of course, are very much the same. The scientific method is that if you have a theory and you have a reproducible experiment as observables, that what you have according to theory and the models that are the physical models attached to the mathematical models, it doesn't hold so, then is falsified. So we basically have that a scientific theory is reproducible, it has observables, and it's falsifiable. And similarly, statistics are the exact same thing. You got a statistical hypothesis, and all you can do from this statistical hypothesis is in the hypothesis you presume or assume a distribution of events that can be sampled, and then as to whether with regards to how it can be quantified, that according to the samples that then are studied in an experiment, whether or not they invalidate the hypothesis. So you got a theory, and whether it's falsified, you got a hypothesis, whether it's invalidated. So in this manner, we kind of make it so that when we talk about our beliefs in these things and the truth of these things, that it's according to so. Because once we've done it so according to the scientific method and our statistical method and the reasonable design of experiments with regards to their controls and the experiments, that it's quite reasonable these ways. So then we call that scientific, and we can say that other things are basically, if they're not scientific, you call them non-scientific. Then there's the pseudo-scientific, which might be super scientific. It's above it, or not necessarily could be so related, like we can't really establish observables, or you can't really establish the falsifiability. But it is still a theory. Can have the high and the low can still be kind of associated with a world of scientific, mathematical, logical, philosophical objects, without necessarily having to have two separate realms or discontinuity. And then there can still be a continuum of these things, and then that whether the Big Bang or the steady state hypothesis, that neither nor is falsifiable and both are, is a thing, and that free will is a thing. So let's continue into the stacks, going back into the stacks. In the university library, you'll find that the mathematics and logic and physics sit in P and Q. And so depending on the size and how long they've been collecting the books, then you'll find something like physical review letters from like the 60s, A, B, C, and D. Hundreds of volumes, primary science. Vis-a-vis all kinds of textbooks, expository counts, specialist inquiries, fields, subfields, applications. Biology starts at A. And there's lots in the middle. So let's find out what we get into in our stack here in the next. Oh, well, first, I went shopping to I got some toys. So this guy is a Newton's cradle, and what these are is it's a little desktop executive toy, and I'm not sure if it's set up or how it is yet. You know, get something, you always want to make sure that it kind of comes out and goes right. But it's just in the world of executive desk toys. This is the cheapo little thing, and how it works is that this fishing line is used what might otherwise have been something like a rigid rods or something like that, and Newton's cradle is the idea that then the momentum from this side will carry through via inelastic collisions and set up the other side. Then as so far the way out, this is not necessarily one that is so much great then for display purposes. But they have better ones, and so this is just something like it's just a thing. And then this other guy here is what's called a gyroscope, and so this is of a particular model and variety. And then what you do is you attach it with a string, and then it sets up as like a top or dreidel kind of a thing, a spinning top, and then it helps to illustrate again what momentum is and inertia, and then with regards to its dynamics and the kinetics and kinematics, how it is and how these things are like so. So that amused me. And it kind of goes well with like the little Zen guard, and then the remains of the old fish tank, the little fish tank. Symbols. All right, see the dawn of Tantra. So here Gunther and Changpa talk about, for example, in this chapter, laying the foundation of the Tantra. So the Tantra is studies. It's a theory from Buddhism, and this helps to illustrate that a lot of the same things for naming things and emphasis on the aspects of the Tantra. The sadhana, that's a method or practice, it says. One of the greatest things about phonetic writing is you just spells it right out, and it helps to establish the pranabindu nadis and so on, breathing practices, and these such matters is usually associated with the methods of structured meditation, and I'm not too familiar with them. I've been learning that something like the apsara is the dance, and the kabak are like, gesticulations of a sort, and it's kind of like a little language and these kinds of things, that there's like all sorts of these, I think they call them still signs today, but they have various purposes for various reasons. Sutra and Tantra, all right, it's the Tibetan names, they're Tibetans, and in the Tantric tradition, ego or confusion or ignorance is personified as Rudra. All right. See, this sort of book really goes into a lot of levels to help associate and attach what's all there from our reasoning and dialectic of Western tradition, which is in a sense a little bit more structured, and it's kind of built after scientism and logical positivism to be a little bit less subject to ambiguity that otherwise is part of the feeling out of the space and how those things go. And he says that the Yogacara has used the concept of the alaya vijnana, a concept which has been used differently by different Buddhist schools, which is very important in the Tantric tradition. The alaya vijnana is already different from the alaya or basic foundation. The latter we assume for the purposes of communication without affirming that is an ontological entity. So it gets into the ontological commitment, an ontological entity, what is a theory of things, what is a strong theory of things. That the foundations, writ large, the study of foundations is like science and mathematics. Where mathematics and logic kind of have their own strong presence, what we call Platonism, a strong mathematical Platonist mathematical universe. And then that things like the tantras help to illustrate that it's the same kind of thing when just studying the same overall philosophical concepts at all. What's learned, what's experienced. So then this gets into what are descriptions of their meditative experiences. And so it's kind of like, as it was said of Zen, it's like, you can't learn Zen. It's like, that's learning something about it, But the idea that then the describing these things help to have that people go through actually mental experiences that are associated with rapture or the epiphany, or these being considered very strong psychological experiences. That as well, there's the notions of the states of being and objective subjective distinction, and the various notions of insight that are associated vis-a-vis developmental stages and developmental experiences and significant informative experiences of all sorts. That then the idea of the study of foundations is to get above all that stuff, to have sensible, fungible, and tractable means to relay and communicate. And according to the scientific and the statistical, that it can be relayed and communicated quite perfectly well without having to establish an ontological commitment or belief, except as besides to shared definitions and derivations. So that's all quite usual. The foundation of the creative approach is openness, shunyata. It is more than the nothing by which it is usually translated. According to Buddhist tradition, this openness is the basis on which we can enrich our lives, the basis of the various tantric practices. So this is like, all such manners of purposeful thinking. And then here is kind of structured as entire concept philosophy, and with like-minded followers around the world and since recorded history. So then with what was the notion there for a second that there was about the nihilism or this and that? This is what it was, the heart essence of the great perfection. So Dzogchen was described as kind of like a dialectic. So this is kind of like Descartes for Buddhists. But it's really kind of from the entire notion of the distinction between the ordinary mind and the Rigpa. So the Rigpa is the ground for Dzogchen. So, and it says that it can't stand for its own, but that's the same argument against Platonist ideals and their objects in his existence. And so Descartes, what happens is he'll say something like, well, besides the holiest or that, then all what we have in our mind is just matters of perception, and so it doesn't stand on its own. Kind of like the Dalai Lama says, the Rigpa doesn't stand on its own. But then he goes directly into an extended argument why it does. So if you read Descartes, what you can find is that once he starts to entertain an idea, then he will consider it from all angles and get right into it. And it ends up reflecting back to his kind of tender reserve, is that it is his opinion, it's his own theory, So that's why I kind of identify these as the same. The dawn of Tantra. This is it. Okay, this holographic paradigm is about quantum mechanics and the questions that arise from quantum mechanics and the statistical interpretation, or what's called the Copenhagen interpretation of quantum mechanics, which is that there's no real deterministic value because Heisenberg uncertainty says that there's only a statistical interpretation. And so a lot of the interpretations that came up with that after the 20s, when the world's leading quantum physicists got together and decided this was going to be the the model and the interpretation of things, was then the idea that still everything's somehow related, and all such manners of the extra local, that in terms of then for what Einstein has, to keep it in the context of differential analysis, that the whole theory is only of a space-time of a differential system, which he has as parameterized by the time, differential system, that then trying to reconcile the statistical nature of things and the deterministic nature of things has that a lot of the concepts of duality, which are so leading to this, in a sense of openness or whatever, is the perestroika and catastrophe. Sometimes openness and catastrophe are the same word in some of these things, but other times they're like the dialectic, or even just thinking about things at all, the mind. That the quantum consciousness of this holographic paradigm gets into both things that reflect what is as of the scientific and super scientific that still has to somehow fit in our theory. It's like the theory dictates that there is a super scientific, so work it up. And compared to that, we have we're each thinking individuals with our own ideas about things. So this is an interview with David Bohm. And so Bohm is familiar for Bohm and de Broglie, and de Broglie was about the time is when Copenhagen interpretation was real. So he kind of argued against Heisenberg. As for Schrodinger and Heisenberg, they're pictures of things in the wave-particle duality and the wave function collapse of the Schrodinger wave equation. That then de Broglie was like, well, no, it's real. It's extra local. Besides that, we have our conceit of the electron physics, and that the substances are particles, the atomic world, as for the subatomic world of things, and all their interactions in the quantum. That the quantum is having made a theory of points of things, particles, not quite points. They're particles with finite values. And then it was totally established all these wonderful facts about the electron physics and the discreteness of and the conservation of these quantities, that they add up, basically with regards to the energies of electrons in their orbitals, and as about the model of the nucleus, and then as about the optoelectronic effect with regards to light of a particular frequency and energy and intensity, and a similar amount of electrons, particles. So light, and again, this is among all these other usual notions of the models of the quantities, things. Light is a ray, light is a wave, particles is waves, ... So the particle-wave duality is one of the first things in physics that really opens it up for the whole notion of complementary duals and thinking things over and this and that. Kind of like Gödel's incompleteness. It's part of our canon and dogma, which before, for example, did not have it. If there's an important thing about canon and dogma, is that it changes over time according to science, largely. Before the electron physics and getting it all together, there was a bunch of different theories, and they each approached the empirical angles from all these different ways. So having one theory where we have like electron physics, then gets in this whole deconstructivist account, why elementarily then we rebuild these other planks, platforms, fields. That for our foundations is one thing, that this is our foundations, our elementary fundamental, the theory, that it comes up kind of that way. Why these days it's getting put back together again, and you can find it in the stacks. So Bohm and de Broglie are named together for having then these theories about the real wave function, and about that, yes, Heisenberg's uncertainty principle is still a thing, and we reason about it and rationalize it because we have limits, and we can't peer between two atoms. That's the scale of where these things kind of let out. But we can still have a theory above to try and figure out the attachment of a theory that then will explain that. Then we need mathematics to have what are the elementary accounts of a deconstruction of the atomistic universe, the stoichiometric for all of chemistry, and the mesoscale, and all the usual laws of physics, from a molecular model to the continuous space-time, its manifold and such. Superstring theory. This is where superstrings are to atoms, the chemicals, Democritan atoms, what atoms are to us in the order of things. So if an atom is about 10 to the 25 smaller than us, the superstring is just 10 to the 50. And then it's just another, it's like effectively smooth. It's grainy, but effectively smooth. Some smooth, it's about the smooth and the rough, Poincare and Euclid's manifold, which is just a continuous surface, a continuum, but with all its folds. Bohm. Bohm is being interviewed by Weber. So Weber says, and even talking about the realms beyond the non-manifest and is therefore going to reflect that confusion. So one mustn't catapult oneself up to those realms, but tackle what to you is the block. Bohm says, yes, that's right. We can bring order into the realms which thought can touch because that's the beginning, and the insight is primarily what is needed to bring that order into the brain itself. And I think that this present positivistic and pragmatic view of science has contributed considerably to the disorder in the brain, because insofar as people take it seriously, they're going to give it a lot of weight. Therefore, it's going to contribute confusion to all that's in the brain. So what Bohm comes up with is that the stochastic Copenhagen approach was kind of the root of this issues, that various naive assumptions attached to classical models run away with themselves. And so he advocates, and he has one of his great books, or out of Bohm, one of his greater later works is called Implicate Order. And it helps to build back that it's this continuous again. It's superclassical. Yeah. And so this just helps to explain at the same time the whole idea of the fourth dimension, which was advocated since like space and time. It's the fourth dimension. Or it's otherwise just outside of our usual milieu of like, I can see it, I can feel it, it's sensory, it's phenomenal, is that there's a realm for freedom of thought, or there's just a free axis, there's a free variable. Similarly with the whole idea of quantum mechanics, it's like, well, it's starting to add up as waves and these things that are combining to form these waveforms, but we can't compute and calculate it in finite quantities because of the ultraviolet catastrophe, that it works best with our electron physics and it adds up. So we can have formulas that add up. Otherwise, it's unclear, according to all these empirical interpretations, what it should be. So getting back above that, then it's called, we have particle wave duality, and then the theory of resonances. So resonance theory is above that. Down to the point, local, global, and total. This is how it's possible to consider a continuum of things as discrete things, that are quantum is an atomization of things for the theory of Democritus and the atom and stuff like that. The subquantum is as of under the Planck scale from Max Planck, and then that he has got some great formulas that add those up. And then the superquantum is this notion of the molecular chemistry instead of the atomic chemistry, that the resonances and stuff add back up, including stuff like Fresnel lensing and this and that. So the quantum just means to make something discrete, so it will add up in these formulas that balance and with conserved quantities, symmetry laws. And then that's just to make it fungible in terms of mathematics. And then these ideas are the theories of higher mathematics that include more and better mathematics of infinitesimals and infinities of the continuum mechanics for the individual of continua is quite a thing. I think I learned that word individua from Umberto Eco. He's a semioticist or semiotician. Studies phenomena, perception there. So Bohm gets back to implicate order, trying to help people get back over a perceived schism caused by the necessary perestroika and opening and duality of particle wave duality into a modern theory with particles and waves. So, I mean, that's in science that they're both already, and resonance theory. So that's coming up a lot these days. Is old rat is new, or same old, or revisiting and the abandoned theories before, and helping to equip all the detail of fundamental theories with the conditions of their surrounds. So helps keep things simple. 200 puzzling physics problems. They're hard. What this is a book with all these great physics problems. So he'll lay out like a story problem and then spend like 5 or 10 pages helping break it down and define it in terms of formulas, and give it in terms of trigonometry and systems of units. This is, of course, for science, the most necessary thing for the empirical is that we attach to our numbers then dimensional analysis, and then so that to each dimension, not just a number, is attached its fundamental physical units: length, time, mass, charge, wavelength of light, frequency of wavelength of the of a ray of lights, photons is the usual way, half-life, these kinds of things. These are usually called the System International, or SI units. And then the way they work with algebra is they keep with the variables, and so any variable with a given kind of units, which is above or below a divisor bar, this per that, any kind of power and order of them, is dimensional analysis. And it's the most first thing that is involved in any kind of setup of a thought experiment or one of these ansatz or setups. Denote the mass of the boron atoms, actually boron ions, by M, and that of the unknown colliding particles by little m. And he has a diagram, and it involves vectors, and it shows what is related in terms of the directions and their orthogonality. Before the collision, the particles have opposing velocities of the same magnitude v naught as measured in the laboratory lab frame of reference. We can easily transform to the center of mass cm frame of the colliding particles shown in figure S93.1. The total linear momentum of the two particles in the lab frame is mv naught minus little mv naught. Thus, the velocity of cm in this frame is u equals big M minus little m over big M plus little m quantities times v naught. Now, I'm not going to read so much more than that, and that was meant to be, just kind of in voce, for this author, who is really pretty great. I'm not sure who all put this together. Peter Gennady, Gyula Honyek, and Ken Riley. But yeah, this is a great book that would go well in any kind of physics class as a source of enrichment. Holographic paradigm. So Kodaira Kodaira is one of the highest level algebraic geometers that sits in fundamental physics and various theories related to Yang-Mills theory and physics' gauge theories that there is. So this is a book of his works between 1937 and 1971. Often they reflect Kodaira's collaboration with other prominent theoreticians, such as Ayanaga, Abe, Kakutani, Chow, Spencer, Hertzbruch, Nierenberg, and de Rham. De Rham cohomology is one of the great integrators that pulls up for de Rham, R-H-A-M cohomology, of algebraic geometry and complex manifolds. These days, a lot of the physics is having seen a great effort to try and rewrite a bunch of it in what's called hypercomplex numbers, but really after Elie Cartan's reflections and rotations. So the whole thing about complex numbers is that they add as magnitudes and they model a rotation. They do well with polar coordinates in one plane around the clock. And so the idea of the quaternions after Clifford and Cayley and Grassmann were the higher order terms with a few more of these roots inside, that then their products model a rotation in 3 dimensions very well, and they don't suffer some of the vagaries of what is the usual milieu learned from computer graphics of the computation of affine transforms. So matrix manipulation is a particular way to multiply in a given order. It's an algorithm the rows and columns of a matrix by another matrix, usually that have on one side that has the same length of that, so they kind of line up, that it always has a well-defined matrix product. But then what you can do is for a given organization of the points of something, that's location, then you can multiply what's called a transformation matrix and then apply any kind of affine transformation to it, which is either and only rotation, rotation, in the plane around a point, translation, left to right, up and down, or as sums of those, reversal, and then skew. It's possible to, from a given basis, kind of skew the whole thing. So quaternions sum that up in only 3 or 4 terms instead, that you can result is like, I want to compute when something rotates by so far, what is this orientation before and after and before. So that's called geometric algebra. There's algebraic geometry, there's geometric algebra, there's the differential geometry, differential calculus. There's lots of these kinds of words that kind of reflect a lot of different things in the fields, and so that said, it's all geometry and operations. So he talks about theorems of completeness. So if you can establish a completeness result, then you can use it to assign a value that's derived from one way via a closed form of another one. Again, reflecting on the great benefit and utility of closed form analysis of things and how they go. A theorem of completeness, on stability of compact submanifolds. Stability is with respect to the stable and astable, that which will maintain as in an equilibrium and that which won't. And then with like global and local, minima and maxima, where a local minimum or maximum will stay at a certain point, but is astable in the sense that under a sufficient excitation or change that it will fall off. Whereas a global minimum or maximum will be that, no matter how you shake it, it will always end up at the global minimum or maximum. So they just kind of reflect state. Compact analytic surfaces, compact complex analytic surfaces. Compact complex analytic surfaces too. On the structure of compact complex analytic surfaces 1. So compact means closed. Complex means analytic with these pointers that kind of point out and over to it, and we can use as up and after forms. And analytic means that they point, right? And then surfaces are, as was described, a lower dimensional surface in a higher dimensional volume. So it's like a line or a dot in a plane or on a line. Pluricanonical systems on algebraic surfaces of general type. From the Journal of the Math Society, Japan, 1968, page 1554. So, finding where that is, 1554. I'm not sure if that's included here, but it's something to follow up in Kodaira's other later works. At any rate, this is he's one of the greats here, the 20th C of Kodaira, and he's very deft with the mathematics of matrices, especially about their adjoints, their conjugates, their determinants, what's called the determinantal analysis. You can get into what are called the generalized matrix products, which are like, besides regular matrix products, you can multiply any matrices together and they'll make a product. What is it? Well, that's lesser defined. This other stuff has got closed forms. Matroids, these kinds of things. Generalized that, where generalized means, I can definitely apply it to the more generalized, whereas forms mean is like, I can close it in this form. So, supports completions, manifolds. It helps to define this coterie of this gamut of the regular terms that help define the state of done. When something is done, you can say a theorem or formula is shown when you reach a certain point where something like a completeness or a lemma is held up, or these kinds of things, according to these usual properties that then apply as much as possible, just kind of smoothly via the operators over the things, elementarily. He mentions the upper semi-continuous, and so that gets into, where it falls out, and then what? Cases. The idea of cases, that the completed has established the full case, and that the coverage covers all the cases. Picard variety. So after Lefschetz and Picard is that algebraic geometry in its terms for algebraic varieties and up to into the simplicial varieties, and these being kind of pseudo, but completions above those. Those are the kinds of things that Kodaira considers. We can talk about them in the present tense because it is. This is a textbook, Probability Theory and Mathematical Statistics. And what it's about is the Wiley Publications in Statistics having that the editor of their series of these 60 books or so are all in this form from Wiley Inner Science. You can kind of see the mark there that they're one of the greater publishing houses of technical works, and you could find this in your university library. Not that this one necessarily is from the library, but in accordance to that, this is the sort of book you find in the library because it's authoritative and peer-reviewed and edited as part of a series by editors who in the sense of the production of higher level books in mathematics and science have kind of particular goals besides the publisher's goals of making money and priority and making a mark of gaining priority as authoritative. So what this is, it's got a bunch of different things about sampling theory and statistics, business research, statistical tables, applications of statistic, analysis of statistics, international trade statistics, elementary statistics, genetic statistics. Statistics is a wide open field with regards to any manner of data gathering and its interpretation. Probability theory and mathematical statistics. Mark Fish of New York University, in this third edition, published in collaboration with PWN, Polish scientific publishers, to Olga and Alexander, says that this book was published, it's called Rachunek Podobieństwa I Statystyka Matematyczna. That's Polish, I imagine. I don't speak it, but the words say that. Library of Congress catalog card number 637554. So many or most published works are collected by the United States Library of Congress. They get copies of pretty much everything that's ever been published. And then that is assigned to work is like a cell. Then these days they have what's called the ISBN, the International Standard Book Number, another usual reference ID for a work. Then in the digital age they have what's called the Digital Object Identifier, DOI. Another it's just a number, and it means this particular book and this particular printing. What the author describes is an introduction gently to the theory of statistics and probability theory. So in the usual curriculums today, what you do is you start with statistics. And so you got to learn the classical probabilities, like rolling the dice and adding them up, counting cards and adding them up. And that's called classical probabilities, and they're from discrete distributions. And then you get into the continuous distributions, which is that over time, how can we figure out how likely it is that something is within a given amount of time? Given accordance to the distribution, the shape of the distribution, because according to like these distributions are just these functions, and all they can do is you put in some numbers and you get out some numbers, and then you integrate up to that point and find out how much weight that is, and then you can estimate the mean and determine if that's according to the estimator what you figure you're going to get. So probability theory. So statistics usually starts with the central limit theorem and the great utility of the central limit theorem for distributions that have a mean. They have like a central value, a centralizing tendency. Because then there's this whole group of results after a fundamental theorem called the central limit theorem, which says that the center builds in the limit over time, and then it looks like a normalized and standardized Gauss distribution, which is called the bell curve, shaped like a bell, and it's got a hump in the middle, and it trails off on either side. And then all those notions of like, well, we compute the variance, and the square root of the variance is the standard deviation after it's standardized and normalized, and then we can count out how far that is off from the mean, and we know that the mean is 50%. 50% above, 50% below, and then counting upwards in the standard deviations, that is 65, 80, 85, 90, 95, 99, ... So then that gets into all the quartiles, and all that stuff is just like, all we know is that all these percentages come up here. Then when we want our confidence interval back, it's like, I want to be 95% sure this will be like so. We just count up this way, find it out that way, figure out that, read it off the table. That's the usual. That's usually what statistics is called. And then the probability theory gets into the whole theory of like, there's a space of events. You sample one. You know, what is this value? There's a distribution of the events. We don't know what it is. So we have a hypothesis. We're like, well, what if it's this distribution and it was like the so, and I start getting these values? How likely it is, you know, according to this, that it wouldn't invalidate my hypothesis that it falls in this range. That's what it is. By hypothesis, the numbers xk are integers from the relation by formula, letting, substituting a variable for another variable, so then it crunches and falls out. Used primarily at first in theory of probability for normalization and standardization, which is where you say, okay, I have a distribution and it's got its scale parameters. I divide out the scale parameters so it's just a unit size, because then I can just try and kind of treat it between 0 and 1. Right? And standardization is similar to that was for variance, which is computing the sum of the distances. Like how would they fall out if you put it in a box and they're all falling back in together. Graphically, yeah. And then the theory of probability necessarily involves a sort of experience with the integral calculus, because almost all the distributions are formulas that are in terms of integrals and derivatives of exponents. And they're like, the good thing to know though, if you want to study probability theory, is you go find a catalog of the known distributions by their scale parameters, and especially their shape parameters, because according to different singularities and minima and maxima and changes in the shape of this distribution and what's under it, the expected value that so adds up to it, is that those are called the shape parameters. So you go find the 20, 30, or 40 different named and known distributions, and then when you have some data that looks like so, you just kind of look and find one that looks like it, and then try to do model fitting on that. You just say, well, at least I can start my hypothesis with something when there's a distribution that is very well known and there's much known about it, especially if it's in the tool, and the tool will do that. Or that these days what they do is they just take any distribution of data and then they just send it. It's like, I'm just going to go ahead and send this to the 500 computers back here, and each one of them is going to try and see which one comes up dice. Some things are pretty simple, especially when you have 500 computers doing a thing. But when it ends up, he's like, well, I'm glad you planned to do it that way, because now you're going to do it on pencil and paper. And then it just, helps to scratch a little bit, how to figure these things out. show that the central moment of order k of simple samples has, as n goes to infinity, the asymptotically normal distribution. So it's essentially a statement of the central limit theorem of a distribution at a given mu sub k of this root of this entire quantity, u sub 2k minus 2k mu sub k minus 1 mu k plus 1 minus mu sub k squared plus k squared mu sub 2 mu squared k minus 1. All that over n, the square root of that. So this gets into this x squared plus minus 1 bits. Mu is the usual name for the mean. Sigma for the variance, or sigma squared. That then for this section, this is the last exercise in chapter 9 about sample moments and their functions. So this is where a probability distribution is either a moment generating function, and they're not as quite as well understood at all, and they have a lot different issues to deal with. Cumulative, or the probability distribution function. I'll often confuse the cumulative distribution function and the cumulative density function, or the probability density function and the probability distribution function. So PDF is a probability distribution function, and a CDF is cumulative distribution function. So the PDF has the density and is like underneath this part of the curve is this much area that if you threw a dart at it at total random and it landed anywhere in it, that would be a good guess. And then the cumulative distribution function is that, okay, from the lesser value to the greater value, between 0 and 1 is a probability it's less than that. Then the moment generating function is another way to say that we can identify any distribution by a unique PDF, CDF, or MGF, because that distribution in its form is well defined by that. Now that some distributions might have more than a unique, and instead that they're more than one distinct probability distributions, is non-standard probability theory. But in the standard probability theory, a PDF or CDF or MGF will define a distribution. And for a PDF, the probability density function, it's integrable. You can compute the area under it. No probabilities are ever negative. They're all between 0 and 1, and it sums up to 1. Because you have the probability is 100%, that a sample will come from its support space, which is the space of all these samples. So that's the first 5 minutes of probability theory class. And it's the same for all the rest then. All right. Order statistics. Now we get into something, because order statistics started reflecting a whole different kind of approach to things. Because like, well, what's coming in and out of these things, and what are order statistics? All right, poverty of historicism. So Karl Popper is when this episode started about the scientific method and observables and reproducibility and falsifiability. Karl Popper was a 20th century philosopher for whom we kind of say that's kind of our current form of the scientific method. But here he's talking about philosophy a little bit differently and socially. About historicism, though, and about whether we lionize and have dogma and the canon and apologetics, or how that's revised and reformed, and then whether sometimes it's good or bad that for this historiography and historicism, that when we're recounting accounts of and for example making deconstructive accounts, deconstructive literary accounts, deconstructive accounts of received texts or otherwise these things, that what I imagine he's addressing is that there are different approaches and tacks to it, and that it's important to consider why we both want things to have their graceful state, and as well have their elegant current state. These kinds of things. About how then to relate the schools of these things as concepts written in history, like so. So let's see what he says here. He's got a picture. This looks kind of like Zeus or something down there. He's throwing 2 lightning bolts or something like that. Maybe it'll say Karl Popper, The Poverty of Historicism, is a devastating criticism of the belief in the laws of history, laws of social development, or laws of progress. So this is just to say that there's something like the philosophies from before of the natural order. This is just kind of putting them down, and it's in the era of logical positivism and scientism. And so mostly when we talk about Karl Popper, all we're taking from him is the scientific method, or making sure that falsifiability is on it. So it's not empirical. It's like it's worked before, reproducibility. It's like also I can break it. It's falsifiability. So that said, though, he's got this. He spent a lot of time on this. From Vienna, born 1902, left Vienna, fellow of the Royal Society. American Academy. But largely, while we, just like we have theories of nature and nurture and evolution, you know, and these changed, what were the dogma, then we still maintain apologetics for what those are. I mean, we don't burn books, you know, we just ignore them in a sense. And so trying to figure out these things is something that he talks about. Here he talks about social technology. The term social technology, and even more the term social engineering, which will be introduced in the next section, is likely to arouse suspicion and to repel those whom it reminds of the social blueprints of the collectivist planners, or perhaps even of the technocrats. I realize this danger, and so I've added the word piecemeal, both to offset undesirable associations and to express my conviction that piecemeal tinkering, as is sometimes called, combined with critical analysis, is the main way to practical results in the social as well as in the natural sciences. Well, yeah, I have to have a good foundation. We already have one. Technological problems. So he would be familiar with what was going on in, like, the schools of the Frankfurt School and Lyotard and Habermas and these authors who provide accounts of like Orwell and these kinds of things in a modern society. You know, why newer isn't always better, or that older isn't always better, or these kinds of things. The status quo. Holistic or utopian social engineering utopia is always the greatest thing that is offered by people who promise results of things in systems of governance. And since the Malthusian dilemma has been forestalled for quite a long time because there's enough food for everybody, and that it's kind of going all right. It was good, and that's where before we had the study of populations, like after a census, even accounting, where accounting is particularly elementary statistic, is demographics. And so you find that you can find different strata and clustering of all these multiple and many variables. All we talked about were single variable distributions, all the multiple and many variables and all the behaviors and things that emerge. Demographics is a study of these things. And so the very notion that you can focus on an individual and tell someone about them is kind of flawed, subject to its own kind of the fact that a lot of statistics and probability only know that there's a central limit theorem. It's like, this is for everything that's got a central tendency. It adds up and we can always apply it. And then the idea is that, well, some distributions have what's called the long tail. They're outliers, things that don't lay within the expectations. So when you talk about the demographics, and then we talk about the individual lens, was like, well, we took that 500 computers and had them follow your every move ever since you got your smartphone 15 years ago. And whether or not that really gets to the person is like, well, I don't know. I don't know that person. It speaks to that there are lots of things that are really part of a correct statistical and scientific approach to these kinds of things, that the theory is still lacking. That besides a central limit theorem, there's a uniformization limit theorem. There's a dual to it. So I would make Karl Popper appreciate that by explaining it to him in science. Deeper into the stacks. Well, so this is about they're kind of like communists, but they're the Habermas and the Frankfurt School, and so I don't read them necessarily as to use. I study them is what it is, and also I appreciate some of their analysis, and because they provide a great amount of critical analysis, which would otherwise go without critical thinking, like groupthink and some of these other notions of the tragedy of the commons or the tragedy of the herd, in terms of like thinking about the herd and the people and vis-a-vis being a part of it or not. It's like these things. Among his influential publications in English are Knowledge and Human Interests, Theory and Practice, The Theory of Communicative Action, and Moral Consciousness and Communicative Action. So we'll definitely say that this is part of like the social, but he is very familiar with the canon and the philosophy of the thinkers. And in this manner, with so few words, he can express a relation that brings this kind of eternal silver thread together along with it. All right. It's one reason why Marx, it was so influential, because not because he was a communist and a voice of the people, is because he could explain to intellectuals the canonical dogma in relation to his edifice. So, George Steiner on difficulty and other essays. Now, I'm not quite sure what's in this. I don't know much about it. George Steiner presents the first systematic investigation of the phenomenology and processes of translation inside language. So this would kind of fit in our studies of it's not differential analysis anymore, really, is it? This is part of the philosophical foreground, but for getting back in this amount of time to then the descriptive differential dynamics is that for another day, that there's more of the stacks here and what to go through. So I haven't read that, but it fits into the literary deconstructive and criticism and how, for example, that not all deconstructivists are ultimately deconstructive. That wouldn't be deconstructive. So some of us are just plain back to structuralists again. This is how things are and how they work and why they should be, and answering all the question words. Let's see here now. So this will have stilled a bit, and I wonder. It's better to have one that is a bit more precise, because what it will do is that it won't immediately reach to where, according to that, these strings are not rigid, and that the precise tolerances aren't necessarily so, that the effect only happens when they're in a perfect line. So that's something to figure out at a later date. But for now, it's just kind of one of those showpieces or something like that. For differential dynamics, then it's still the identity dimension. It's a primary concept related to the manifold of quite a usual large number of systems. In importance, after the notion of zero and the origin as being singularity and included or excluded from the envelope, or being part and parcel of the coordinate setting of things, is that then this whole idea of the identity dimension helps refine the Cartesian notion usually, and all the great things that become tractable after becoming fungible and sensible, the coordinate analysis, which was mentioned, is so related to dimensional analysis and analysis of units and all such things that remain quantitative, that the identity dimension is a pretty neat thing. And so I'll be coming up with some more about that later. With regards to my goal, which is to implement the stop derivative or derivative stopping with respect to that and pseudo momentum for all such matters as would be applicable in mechanics. Descriptive differential dynamics, now and less. Hey, have a great day.